Let's go to the second talk of this session. Dr. Ilan Plante. Her talk already has been advertised. She's a senior scientist at Nanosys. She works on the next generation of displays, leads a research team there, and is aiming for a 1 million nits of brightness display. So she will talk about very stable quantum dots and maybe bringing quantum dots on chip. So the floor is yours.
Thank you for the introduction, and thank you also for the invitation to speak here today. I'm a senior staff scientist at Nanosys, and for my talk today, I'm going to be explaining some of the ways in which quantum dots are solving the display challenges of the future, and what we've been doing as a company to continue to advance these materials to meet coming challenges. So first off, a bit about Nanosys. We're a company that focuses on enabling the future of displays. And one of our core competencies is in quantum dots. And in this realm, we are the world's leading quantum dot supplier. We've brought this up to scale to greater than 100 tons of annual capacity. And we've really grown the market opportunity for these materials. So at this point, since 2013, there have been nearly 1,000 SKUs of consumer products that have been released. In addition to this scale up and this growth, we continue to focus on R&D. And there we have a patent portfolio of over 900 patents worldwide, both granted and pending. In addition to quantity, there's quality also. Our customers represent all top 10 of the global television makers and 4 out of the top 5 IT makers. So what is it about quantum dots that make them so amazing for displays? Quantum dots are really one of the best materials out there for color engineering, and there are a few different reasons why this is. First of all, they're super efficient emitters. Their quantum yields can range between 90 and 100%. And their other amazing property is the tunability of their spectra. They have super narrow line widths, and you can change the emission color everywhere across the visible and beyond, with tunability of plus minus 2 nanometers of resolution. Together, this combination of efficiency and color tunability make them some of the best for achieving high color gamuts in displays. And this is not just something that's a flask in a laboratory anymore. This is truly at scale, and Nanosys has done a lot here. These are produced in our facilities, again, at those hundreds of tons capacity, matching the performance of those materials made in the laboratory. Beyond the amazing color that they have, there are a number of other properties that make them particularly suited for displays. Some of this is the excellent operational stability when operating under high brightness conditions. So brightness is a necessary element for displaying high dynamic range content. Partially, this is so you can see your screens under ambient light conditions, and partially this is so you can see true lifelike imaging when you have natural scenes, like sunrises and sunsets, for example. Quantum dots also have incredibly fast radiative rates that make them excellent for displays. I think this came up in the earlier session. The incredible quantum confinement in the system means that the radiative rate happens on the order of tens of nanoseconds. So this is super fast, and what this means is when you turn on the pixel, it turns on right away, and when you turn off, it turns off right away. Your display is crisp and responsive, and you don't have any ghosting either from fast-moving objects or scrolling through text. So Nanosys really opened the door here for this technology, and QDEF was our first technology that came up to scale and was released. QDEF really enhances both the color gamut and the efficiency in LCD TVs, and it's made it incredibly competitive with OLED, both on the performance of the display, but also in the sense of commercializing, in that it's in a low-cost package and requires no CapEx investment from the display manufacturer. Over the course of its lifetime since its introduction, it's really become a dominant technology for enhancing display color enhancement. And at this point, since 2013, I think we have, over 60 million TV units shipped of these products. At this point, it can be done with heavy metal-free materials. Jason Hartleb talked about this a little bit earlier in his talk this morning. This helps make them compliant with regulations that are out there and more ecologically friendly. So QDEF was really just the beginning of quantum dots, and if you look at our display roadmap here, you can see that beyond QDEF, which was introduced in 2013, we've more recently introduced XQDEF. So XQDEF utilizes our air-stable quantum dots to be able to make QDEF with barrierless films. And being able to do this lowers the cost of the product and really opens market adoption. Next up in our timeline is quantum dot color conversion, or QDCC. And this can be done either with QD OLED, so blue OLED backlights, or with micro LEDs. There are a number of different advantages here, both the efficiency and the manufacturability. I'm going to talk about that later in this talk. Further off into the future is nano LED, or electroluminescent quantum dots. And success in this area will finally enable ultra-thin and flexible devices. So for the majority of this talk, what I'm going to focus on is QDCC, or quantum dot color conversion, both the efficiency gains that you can have from it, as well as the manufacturability. And then I'm going to talk a little bit about the future-looking challenges for this area. And that's primarily in increasing the flux, the blue excitation light source that goes into emitting. First off, QDCC. People have used this phrasing earlier today, and I think it's really the most accurate. It takes the best of two worlds and it brings them together. So quantum dots plus either blue OLED or blue micro LED. From the quantum dots, you have super amazing color, super high brightness. And then from either the OLED or the blue micro LED, you have that perfect viewing angle and the blackness levels, right? So it takes each of these technologies and it brings them together into one. When you consider quantum dot color conversion on blue OLEDs, there are huge efficiency gains to be made. It gets rid of wasteful color filters, and it eliminates the need for a white OLED pixel. In addition to the amazing color and things that your consumer can see at the end of the display, there's also a lot that happens behind the scenes in terms of the efficiency and manufacturability of using this technology. So some versions of this slide have been shown before, and this is from Eric at Yole. And what this is showing is about the manufacturability of micro LED displays. And specifically, as you go to larger formats that have thousands of pixels, if you need a really, really low defect rate in this system, and you have to do multiple of these transfer processes, you can have quite a few damaged pixels in your final system. And there's a combination both of cost and expense in repairing them, and also the time of doing this. Moving from a 3-color micro LED to quantum dot color conversion on blue only can simplify this process. If you're only transferring the blue chips, you can actually do it in a monolithic process. And then as a secondary step, you can convert 1/3 of those pixels to red and 1/3 of those pixels to green. Depending on the actual pixel size that you're talking about, the patterning of the quantum dot layer can be done in a number of different ways. This can be through inkjet printing for larger pixel sizes, or through photolithographic techniques for smaller pixel sizes. Because you only have the blue chips in the background, this addresses some of the issues that were brought up before about the complexity of the driving electronics and those different current densities required to run the different micro LEDs. If you're only using the blue chips, you can really simplify the electronics of the system. The last thing here is really enabling, and this is about the efficiency of the micro LED. And this becomes more and more important as you talk about moving to smaller pixel sizes. So smaller pixel sizes come into play in a number of different future display technologies. So first of all, if you're talking about moving to small format displays, if you're trying to maintain really high resolution in the system, you're going to have to shrink the size of the pixel. The other is, even for these larger format displays like televisions, epi area is expensive, and being able to shrink your pixel size is important for cost savings on the display. In any of these cases, these smaller micro LEDs start to run into difficulties with the efficiency, and particularly on the red. So in the example on the right here, you can see that by using quantum dot conversion on 2-micron sized micro LEDs, you can actually increase the efficiency of performance by an order of magnitude. So this is huge. And this, again, really comes into play when you're talking about these small pixel sizes. So I'm really excited to be able to give this talk this year. I think this came up earlier. So quantum dot color conversion has been a topic that's been discussed for a number of years. And every year it's been the same question, when is it coming, when is it coming? So I'm excited to be here this year when I can say that quantum dot color conversion is in fact here. The displays are available. You can see them in the hallway at our booth. And they're really amazing. So many of the top display makers launched televisions in 55 and 65-inch sizes using this technology. So this is quantum dot color conversion on blue OLED. They were the talk of CES when they came out in January. There's also been gaming monitors that were launched in this segment. And they're really delivering on these two promises, so on brightness and on color gamut. So I'm going to get into some of the details of what that looks like. So these are three of the top displays and some of the different technologies that are out there. And these are measurements that were taken by the website Ratings. And what I'm showing here is the amazing color gamut that can be achieved with quantum dot color conversion on OLED. So that top line there that's highlighted in green, you can see it has absolutely the best performance in two different color gamut spaces, DCI-P3 and Rec 2020. And you again saw from earlier, that plays into the brightness perception for viewers and consumers of these displays. Everything is not perfect. There's still room for improvement. So quantum dot OLEDs have this amazing color gamut coverage. They're not yet as efficient as quantum dots coupled with mini LEDs. So you can see in the column for peak HDR brightness per power consumption, so nits per watt, they're still outcompeted by quantum dot QDEF with mini LEDs. There's a lot that's still coming here. Some of this is from other technology drivers. Some of this is from us. From the blue backlight itself, so from the blue OLED, higher EQEs will be coming. There are also a lot of optical games that you can play inside the subpixel cell itself. But then what's most exciting to us is what you can do from the material side. So on the material side, there are new and improved green quantum dots that are coming. I'm going to describe some of those here. So you learned a bit about this topic already from Peter Palamaki's talk in the morning. The QD OLEDs that are out there right now likely still contain a green OLED as part of that green subpixel. And that's probably due to the deficiencies in the green material right now. So the QD OLEDs that are out there today are heavy metal-free quantum dots. These are based on indium phosphide. And when you use indium phosphide as a material, you have to grow shell layers around it. So even when we refer to it as indium phosphide, it's really a heterostructure of indium phosphide with wide bandgap semiconductors on the outside. So there's zinc selenide and zinc sulfide that surround the indium phosphide to make it efficient. If you compare between the green and the red, there are fundamental physical differences between them. And those fundamental physical differences cause differences in the per quantum dot or per thickness absorbance of the material. If you can't absorb all the blue photons, you can't convert them all into green or red. And you see that as a decrease in the efficiency of the green relative to the red. So if you look at those two first rows on that table, you can see the red has a 38% PCE or photon conversion efficiency, whereas the green is only at 30%. Nanosys has been working on a new material, which is very close to commercial release. And we've talked about it in other talks before. This is a ternary alloy core. It's a completely different material from indium phosphide. And because it has fundamentally different physical properties, you have a much higher absorption on a per quantum dot or per thickness basis. That increase in the absorption of the blue photons leads to a huge increase in the efficiency of the material, and you can see that we can achieve numbers as high as for the red indium phosphide. So that's the current status of QD OLED, but as I mentioned before, Nanosys is always looking to the future and trying to address the coming needs and challenges that we see. So I think the next area that's facing quantum dots that we can work on is the higher flux levels that are going to be required. So partially this is from that trend that I was talking about. As you shrink the pixel size, the blue excitation flux is going to go up. And partially this is from new technologies that are coming out. So augmented reality, which may have to operate under truly ambient conditions, or virtual reality, where one of the important aspects of this is delivering realistic imagery. So true lifelike realism to the user. To be able to display high dynamic range content with true realism requires that some parts of the display may need to be as bright as 20,000 nits. So the purpose here is not to blast the user with bright light the entire time. But if you want to see certain scenes, for example, sunrises, sunsets, fireworks, or even reflections, you actually need this huge range and difference in the brightness that the viewer is seeing. So together, these two factors drive a need to have our materials maintain both efficiency and operational stability under higher blue light excitation flux. So what actually happens to quantum dots when you turn up the flux? So this graph that I'm showing here, first of all, it's log. On the x-axis, you have flux. The units I'm using for this talk are milliwatts per square millimeter. And if you look at the y-axis, what you're seeing is the chance of forming a multi-exciton state, in this case, a bi-exciton in your quantum dot. I'm going to talk about these a little bit later on. So for current displays like televisions, these operate at blue flux levels between 0.1 and 1 milliwatts per square millimeter. And if you look at the y-axis, the odds of forming a multi-exciton for our materials, so for red and green indium phosphide-based quantum dots, are incredibly rare. If you look to these displays of the future, though, and you're talking about reaching these 20,000 nits and beyond, the estimated flux levels are between 1 and 50 milliwatts per square millimeter. And suddenly, you can see there's a huge chance you could now be 1% of the time generating one of these multiply excited states in your quantum dot. So what is a multi-exciton? Under typical operation, on the left side of this slide is what happens to a quantum dot. So a blue photon comes in, the quantum dot absorbs it, it excites an electron in the system, and you form an exciton. Under normal operating conditions, this excited state relaxes, hopefully radiatively if you have a really high quantum yield. And this happens quickly, like I told you before, so on the order of 10 nanoseconds. If you crank up the blue flux, there is a chance, and it goes up, that you can absorb a second photon before that first excited state has relaxed. And when you do that, you can form a state known as a bi-exciton or a multiply excited quantum dot. In and of itself, this multiply excited state is not damaging, but the way in which it can relax can cause states that can cause damage later on. So one of the things that can happen in this system is you can have a process called Auger recombination. So one of those excited states relaxes and transfers its energy to either the electron or the hole of the other partner. And once you have that highly charged electron or hole, it can actually leave your quantum dot and go out to an acceptor species that's in the environment. If it does this, what you're left behind with is a charged quantum dot, and as long as your quantum dot remains charged, it remains non-emissive. In and of itself, that might not be the end of the world. Some of these processes can be reversible if your quantum dot discharges and neutralizes. But these really highly excited charges also have the capacity to do redox chemistry. So they can come and they can do reduction or oxidation events, both on the inorganic portion of your quantum dot and on the organic shell itself. So these are the types of events that we want to prevent. So at the start of this project, we went and we did a baseline look at where we stood with our materials, and we wanted to look at those two factors that I was talking about. So first of all, the efficiency of the material under high flux, and second of all, the lifetime of the material under high flux. So in terms of the efficiency of the material at high flux, we're actually in really good standing. So the graph on the left is the emission intensity as a function of flux between 1 and 100 milliwatts per square millimeter. And you can see that that intensity scales linearly, which means that your quantum yield is maintained even at those high flux levels. On the right-hand side is a different type of graph. This is again log, and that's the lifetime of the material, or the time in hours it takes for it to reach 90% of its original brightness. And you can see that as you turn up the flux here between 10 and 100 milliwatts per square millimeter, your lifetime gets shorter. And not only does it get shorter, it is a log plot, it gets shorter quadratically with the excitation flux. So by the end of this, when you're up at 100 milliwatts per square millimeter, that's a lifetime to 90% that's under 10 hours. So this is the current starting point where we saw it. One other thing here, the fact that this is a quadratic dependence on the high flux really strongly implicates those states that I was talking about, those multiply excited states, because they also form with a quadratic dependency on the flux. So it's a clue to us of what to go looking for. So we wanted to improve from that starting point. So we had a few different strategies of how to do this. So there's two main questions that we asked ourselves about our materials. First of all, okay, the flux level is set. If you're operating at a given flux level, can you decrease the number of multiply excited states that you form at that flux level? And then the second question or approach and hypothesis here is if you do form one of these multiply excited states, can you at least promote a relaxation pathway that's less damaging to the quantum dot? Can you do something with that excited state that's less likely to cause permanent harm? So for the first question, can you make fewer multi-excitons at a given excitation flux? The answer is yes, and it has to do with what I was describing before about being able to control the relative volumes of the core and shell components in your material. So by controlling how you build up your heterostructure, your emitter, you can dictate in the material the absorption cross-section. So for each quantum dot, how many blue photons it absorbs. And there's a schematic of this on the right side of the graph. So on the left side, you can see if you have very few quantum dots absorbing all of your light, you actually have a fairly high chance of forming these multiply excited states. And if you move to the right side, if you change the absorption cross-section of the material and you have more quantum dots handling those incoming photons, you share the workload across them, and you actually form fewer multiply excited states in that system. And sure enough, making these changes to your quantum dot structure does have an impact on the high flux stability. So that's what's shown in the graph on the left. So that's integrated emission as a function of time. And you can see the left triangles there correlate to the diagram on the left. That was the starting point, really fast decay. And as you decrease the absorption cross-section of the materials, you can actually extend the lifetime of the materials under high operating flux by an order of magnitude. So the second question was more complicated. The second question is, if you form a multiply excited state, what can you do with it? And here we delved into more complicated photophysics, and we were really lucky to be able to partner our expertise in quantum dot synthesis with collaboration with professors David Kelly and Ann Myers-Kelly at UC Merced. And they're experts both in photophysics and spectroscopy. And we're able to combine our synthesis and their measurements to be able to build up a model of what can happen in our system. And specifically, and these are some of the citations of the papers that have come out from this collaboration, what we saw was a unique photophysical property, and this was a photoluminescence rise time. And this rise time, which happens on the orders of hundreds of picoseconds, so super, super fast, you need really excellent instrumentation to be able to measure this. We were able to correlate that with a transient hole trapping mechanism in these materials. So typically, if you think of an emitter, charge trapping is not something you want to hear, because if you trap a charge, it's possible to open non-radiative pathways that are not typically available. But in our case, the hole trapping that we observed was temporary, it was transient. And when you had this process, you can actually change both the relaxation rate through the Auger process, which we want to prevent, and you can also modify in that Auger relaxation pathway whether it chooses to excite the electron or the hole. Being able to modify whether it excites the electron or the hole and slow the overall rate improves the lifetime of the materials under high flux. So it's something we really wanted to investigate further. We had some evidence that it correlated with the amount of non-stoichiometric indium that's in the system. So non-stoichiometric indium is indium that we can't match to a phosphorus partner in the core, right? So if you do elemental analysis by either ICP or STEM EDS, you can see that there's more indium in the system than you have phosphoruses. We could identify where it was in the structure, and what we wanted to do was to really be able to come up with an accurate chemical model of what the system was. So in addition to the spectroscopy that's on the left, we did density functional theory modeling of the types of states that might form with certain chemical compositions. And what you can see here is really fresh off the presses. This was just accepted in JChem Phys. You can see our chemical model of what this transient hole trap is. So in the diagram on the left, you have the highest occupied molecular orbital of a pristine zinc selenide cluster with no defects in it. And in the diagram on the right, you have that same highest occupied molecular orbital, but it's of a zinc selenide that has an interstitial indium substitution, and it's also missing a zinc, so it has a zinc vacancy. And when you have that system, you can see that your charges are very localized, which is characteristic of one of these hole trapping states. So together, we were able to pretty conclusively identify the chemical model of what we were looking at. And again, I told you it helps to improve the high flux stability of the material. So that's what I'm going to show you here. Since the start of this project, where I was showing you degradation that happened on the order of hours, these are the current lifetimes of some of our red and green indium phosphide, zinc selenide, zinc sulfide quantum dots. So these are now lasting thousands of hours. The excitation flux is 5 watts per centimeter squared. So this is 4 orders of magnitude higher intensity excitation flux than what's typically used in televisions. This is a huge increase in the excitation flux. The green has fundamentally different photophysics than the red. It's currently lagging slightly, but we have a lot of different strategies for both of these materials that we're still working on, and we're super excited about the progress that we've made so far. So that's the end of the data that I wanted to show you for this talk. At this point, I'm going to give you a conclusion. I hope I've been able to share with you that quantum dots, and specifically heavy metal-free quantum dots, have amazing properties for displays. Pure colors, high efficiencies, super fast in response times. When you think about what's coming next, both shrinking the pixel size of micro LEDs and looking at VR and AR is going to require that we turn up the excitation flux. When you turn up the excitation flux, you can open these new photophysical pathways in your quantum dots, and those can be damaging to the operational lifetime of the material. In our work so far, we've been really looking at the fundamental operating properties of what's going on with our quantum dots, and it's led us to large advances. We're going to continue working on our materials, as always, and enable the future of displays. That's it for the talk today. Thank you for your attention. I'm happy to take questions now or in the networking sessions that happen later. Thank you.
Thank you, Ilan, for a wonderful talk. Really nice to see how quantum dots continue to become better and better and be able to withstand higher powers. I already see a question.
Really nice talk, Ilan. Thank you very much. And I'm glad to see companies still doing really fundamental research on this to improve material properties. One of the new things that I learned, because I've seen a similar talk before, is that you can basically spread out the workload by decreasing your absorption cross-section. So my question is kind of how do you achieve that, if you can share that information, and do you see any other effects as an artifact of doing that? So it comes to mind, well, maybe you just want to eliminate zinc selenide in the shell because that absorbs some, so you do a shell without zinc selenide. Well, that's not going to be a good thing for the quantum dot quantum yield or stability either. So how do you achieve the lower absorption cross-section and maintain the other properties that you don't want to get rid of?
Yeah. It is a fine balance. That's where the art of quantum dot synthesis comes from. It's exactly as you're saying. Zinc selenide does absorb blue light at 450 nanometers, so having any of it be present in your material increases the absorption cross-section. In the ideal world, you would have just a zinc sulfide shell. That's not possible, right? In addition to the physical properties of the materials, there are materials properties, right? So there's the lattice spacing of the materials, and indium phosphide and zinc sulfide do not like to make direct interfaces with each other. It's the same as in epiland, right? You can't just grow any material on another material. It's also difficult. You're talking about growing 2,6 semiconductors on 3,5 semiconductors. Alloying between those two layers is really difficult. So you don't have the same flexibility in your synthesis that you would in a system where you can have greater alloying. So you're between a rock and a hard place, I guess. You want to minimize it as much as possible. You can't sacrifice on any property, so you optimize the best that you can.
Okay, thank you.
Other questions? Yes.
Thank you. A question related to the photostability you showed. So it's known that also these properties depend a lot on your solid loading, for example, layer thickness, which is then in the end a very important metric for if you want to apply it for micro LED or OQD OLED. So for the data you showed at 5 watts, how is that linked to solid loading or an absorbance or layer thickness? In what kind of form factor is that tested?
Sure. This is a fundamental study on the materials properties, so these are not under true QDCC conditions. So these are not in patternable solvents, and they're not at the thicknesses of QDCC. The differences here are what you can actually do on the inorganic portion of the material to make it more fundamentally stable against flux. We have separate programs that are ongoing right now that do look at the exact conditions of quantum dot color conversion. There's some exciting work there. I did not include it in this talk because I was talking about the basics. But yeah, you're exactly right. It's a combination of the ligands that are on the quantum dot surface and the matrix around it. And we have some exciting results there, but they're not in this talk. Yeah.
Okay. If you can share them later, that would be fine as well.
Sure.
Thanks for your response.
More questions? In the back.
Hello, thank you for this wonderful talk. Also have a question about this, the two ways that you have achieved to have better photoflux stability. Do you, in terms of priority, do you have a, how do I say, which one have the more influence on the stability? And also about the second question about the absorption cross sections. Does that impact actually for the micro LEDs where you need color conversion with a lower thickness possible? Won't that be even make the film thicker?
Sure.
Thank you.
I guess the first question was about the relative balance of improvements from each one. And they both contribute significantly. So I think I showed an order of magnitude improvement from one and an order of magnitude improvement from the other. On that, basically, we need every knowledge and knob that we have to improve this, right? So they are complementary improvements with each other. They're not competing changes to the material. But I think like what Peter was bringing up, there are limitations to each of these, that you have to be simultaneously maintaining everything about your system that you know and love, the quantum yield, the line width, everything about it. So there's a tight balance of everything you can do on the core shell structure. The other question was about the absorptivity of the material. In the case of the indium phosphide reds, it's less of a concern than the greens. They're pretty strong absorbers, and again, that has to do with the relative volumes of the core versus the shell. So the indium phosphide core in the red materials is a very significant portion of the entire system, and it's the best absorber. It's the most efficient absorber on a per volume space. So there's actually a lot of room to play for the indium phosphide reds. What hurts the indium phosphide greens on quantum dot color conversion actually helps them on high flux stability, right? So they're a lower absorption cross-section material. Exactly what makes them weak also makes them better at high flux.
It's nice to see so much discussion. Are there more questions? And I have a curiosity question that you may not be able to answer. You, and also this morning, Dr. Hartloff mentioned that you have over 100-ton capacity of production. Now, it's nice to have that capacity. That means how much you can make, but how much do you actually do make? So what is the production? That's a
question for our business and marketing team.
Yeah, that's what I thought. It would be just nice to see if you make...
I do not have the answer for you, actually.
Okay.
Yeah.
It's just nice to say you have a 100-ton capacity, but if you only make 5 tons, then...
I think let's find somebody from business and marketing during the networking session and see.
Okay. Yeah. And then another curiosity question, 5 watts per square centimeter may seem very impressive, but in white light LEDs for lighting, we're talking about 1 watt per square millimeter. And so how far are we away from having on-chip, because that was also brought up this morning, on-chip quantum dots for lighting?
So these are not for on-chip. So in quantum dot, yeah. So I think perhaps we've backed away from the need for on-chip. So I think a lot of the desires for on-chip use of quantum dots centered more around cost than they did around a display attribute for the consumer. So I think in general, the industry at large has kind of backed away from the need for that. I think the issue also came up about the color uniformity of being able to do it, especially as you shrink to mini LEDs and beyond, that I'm not sure that it's necessarily such a driving force right now to be able to achieve those for display specifically. I think you'll hear next for solid state lighting. It's a completely different story.
I see no more questions, and let's thank the speaker again for a wonderful presentation.
Thank you.